Welcome to 6.3 Introduction to Significance Tests. Today we are going to introduce the concept of a null and alternative hypothesis, and we're going to talk about p-values, how to interpret them, and how to draw conclusions from them. So first, let's get into some vocabulary. We have our null hypothesis, which we denote as H subscript O. It is the claim being assessed in a significance test. Now, I do refer to this as a significance test. Sometimes I call it a hypothesis test. Exact same thing. Usually the null hypothesis is a statement of no change from the traditional value, no effect, no difference, or no relationship. So when you are reading your question, the null is typically what they tell you to be true, what their claim is, what they are saying is happening for the population. That's going to be our null hypothesis value. Now, the alternative hypothesis is what you are testing, and it's what we should conclude if we find the null hypothesis to be unlikely, and we denote that as H subscript A. Now, there are two options for how your alternative hypothesis could look. It could be one-sided or it could be two-sided. Now, within one-sided, you have two options. We're interested in the deviations in one direction. So either are we interested in all of the values above a specific value, or the values below a specific value. And we will write it as HA, parameter greater than value, parameter less than value. Now for us in this unit, we're working with proportions. So our parameter is always going to be P, and P naught is going to be replaced with that claim we get from our null hypothesis. So whatever proportion they are telling us to be true, that's going to replace P naught for all of these cases. Now for a two-sided test, for a two-sided, two-tailed alternative hypothesis, that's when you're interested in deviations in either direction. So you don't care necessarily if it's greater than, if it's less than, you just want to know, is it different at all? And the way we test that is by doing not equal to. Again, P is our parameter because we're going to be dealing with proportions. P naught is going to be the claim from the null hypothesis. Last thing we're going to talk about is what is a p-value, and that's the probability of getting results as extreme or more extreme, that's why we have these shaded regions, in the direction of the null hypothesis by random chance alone. That's really important. It's us creating sampling distributions and determining the probability of getting these values just randomly, just due to sampling variability. And one thing that I have highlighted is we're working under the assumption that the null is true. We build sampling distributions in the world where their claim is true so that we can see what's the likelihood of this actually occurring if that were to be true. And it helps us support or argue against their original claim. So how do we set up a null and alternative hypothesis? Well, previously we've used confidence intervals to estimate a population parameter. Now we are going to use a significance test. It's another inference method that assesses evidence provided by data about a claim. So we will get into the actual calculation next lesson, but for now we're going to do a lot of the setup. First, a null hypothesis takes on the form O is equal to parameter equals value. And again, remember for us in this unit, parameter is P. The alternative hypothesis takes on the form HA, parameter is greater than, less than, or not equal to the value. And our value is going to be replaced with P naught, which is that original claim from the question. And hypotheses always refer to the population, not the sample. Always use P, or eventually when we get to means, mu. Don't ever put p hat or x bar in your hypothesis statements because that is incorrect. So our first example, Caleb claims he makes 85% of his free throws. Kai believes that he makes less than 85% and wants to test Caleb's claim. So first, let's define the parameter. Remember, parameter is talking about the population, so you should be deciding between p or mu, and in our case, we have a percentage, meaning I'm dealing with proportions, so I have to use P. So I'm going to define my P to be the true proportion of free throws Caleb makes. Now the null hypothesis is going to be the claim, the original proportion that we believe to be true, and that's Caleb's claim of 85%. When you are writing your hypotheses, you want to make sure you write it as a proportion and not as a percent. So I wrote it as P is equal to 0.85. Yes, you have to write HO. Very important that you indicate this is the null hypothesis. Now, the alternative, Chi believes that he makes less than 85%. So my alternative, what I want to test is the true proportion less than 0.85? So I have my parameter defined, I have my null, I have my alternative. So you have done the setup for a significance test. You're going to go through the mechanics of calculating a probability, which we get into in the next lesson. Now you have a probability. What do you do with it? We have to interpret. So significant tests tell us if the sample data gives convincing evidence against the null and favors the alternative hypothesis. And this probability measures the strength of the evidence against the null hypothesis, and it's called the p-value. Now, small p-values are convincing evidence against the null hypothesis because the result we get is unlikely to occur if the null is true. Large p-values give convincing or fail to give convincing evidence against the null hypothesis because the result we got is likely to occur by chance alone. Now, we've kind of touched on this briefly whenever we are interpreting probabilities in sampling distributions. Small percentages, if I have a percentage typically less than 5%, I say that that's very unlikely to occur, and it makes me suspicious of their claim. Because if I have a 1% chance of something happening and it happens, that leads me to think that maybe their claim isn't true. Whereas if I have a 25% chance of something happening, I think, well, yeah, it was just random chance. It happened due to sampling variability. It has such a high percentage of occurring. I shouldn't be surprised that it did happen. So one thing I also want to note here is we don't ever say that we disagree. It's either they gave convincing evidence or they failed to give convincing evidence. We don't ever say we accept the alternative or we agree with the alternative. We're always going to answer these questions in terms of the null hypothesis. So, Leah read an article about high school students not getting enough sleep. The article stated that 87% of high school students got less than 8 hours of sleep. Leah wants to know if this is true at Richardson High School. So first we define our parameter. It's the true proportion of RHS students who get less than 8 hours of sleep. We're going to state our hypotheses. Well, we know that the claim is 87%. So my null hypothesis should be P is equal to 0.87. Well, Leah wants to know if this is true at RHS. She doesn't necessarily care if it's greater at RHS or if it's less at RHS. She just wants to know, is it different? And when that occurs, we say the alternative is P not equal to 0.87. So is it just something other than their claim? And we get some calculations. She asks an SRS of 150 students if they get less than 8 hours of sleep at night. Of the 150 sampled, 110 said they get less than 8 hours of sleep at night. Significance test is performed. P-value of a very, very tiny number is obtained. Interpret it in context. Well, first, I kind of want to make a note here. The p-hat, the sample proportion that I got, is 110 out of 150, which is approximately 0.7333. And we will, again, get into the mechanics of all of this. But now that I have a p-value given to me, I can say, well, assuming that we live in the world of the claim from the article, assuming that the true proportion of high school students who get less than 8 hours of sleep is 0.87, there is a very small chance of getting a sample proportion of 0.7333 by random chance alone. So if I'm living in the world where their claim is true, the chance of me getting my sample, the 110 out of 150, is 0.00000065, which really discourages me from believing their claim. Going into that, Statistically significant. After performing a significance test, you have to draw a conclusion. We're either going to reject the null or fail to reject the null. Again, we don't ever talk about the alternative. We don't agree. We don't disagree with it. We're always going to speak in terms of the null. If we get random results, or if we get sample results that very unlikely to happen due to random chance alone, we reject the null. If we get sample results that can be explained by random chance alone, we fail to reject. So to summarize, small p-value, reject the null, evidence for the alternative. Large p-value, fail to reject the null, no convincing evidence for the alternative. So significance levels. The threshold for what we consider to be small and large is dependent on a significance level. Typically, it's going to be a alpha level of 0.05. And I will say, if it's never given to you what the alpha should be, you work with 0.05. Sometimes the question will change it, but the common one that is used is alpha of 0.05, and that's just a fixed value that we will regard as the decisive value to determine if the p-value is small or large. So we're going to compare it to 0.05, and that just means that we need data so strong that it would happen by chance less than 5% of the time. Last example, looking back at our p-value in example 2, is there convincing evidence that the proportion of students at RHS who get less than 8 hours of sleep is different than the article claims? Well, our p-value was very, very small. And since it's so small, we are going to reject the null. We're going to say that there is convincing evidence that the proportion of RHS students who get less than 8 hours of sleep is different than the article's claim.